it's not clear where your minus sign is, for example.
Right here?
The bar should go all the way across the minus, right? Just to be clear.
So this should be like this, you mean?
Yes.
Okay.
Okay, and then I want you to do another step to show that it's 0. And also 0 should have a bar over it.
Okay.
Okay. Actually, the step I wanted was a plus minus a under the bar.
Okay.
Just because, again, you only know how plus, you're really trying to show that minus sign works the way it's supposed to. Equals 0 bar. Okay. And then at some point earlier you would have shown, okay, and so for the distributive law...
I don't know why I went to pluses.
Okay, you're not quite finished with the distributive law also. You need one more thing at the end.
I kind of messed it up actually looking at it now.
Okay, so yeah, this is some things are reversed. So I think once you start over from scratch with the distributive law, because you even on the left you're not starting in the right place.
Okay.
In fact, the starting place is the second thing you wrote down.
Okay.
So the one that Chris is working on is maybe the most weirdly subtle one, in that you have to be careful about the placement of your bars, which is why I wanted that one to come up here.
What question is that?
This is 14. I know it starts with 4. No, it's not 14. What is it? 19.2. 19.2. Right. That's to check all the axioms. No, okay, Chris, you're now writing out. You've just written out what you're trying to prove.
This is where I'm trying to get to?
Yes.
Okay.
Yeah, so put that down below somewhere, right? I mean, that's what the distributive law would tell you. Philip, red is not working.
Black was pretty bad.
Yeah, we got maybe a better black. Somebody's got a better black there. Okay, so while Chris is working on that, why don't we come over here, look at what Eric did. Okay, Eric, why don't you explain?
I'm supposed to prove that x, the equivalent class of x, times the equivalent class of y is equal to the equivalent class of x times y. And I took a cue from the book and did that. I showed that if x, the equivalent class of x is equal to y, the equivalent class of w is equal to the equivalent class of p, then the equivalent class of xw is equal to the equivalent class of yp.
Okay, let me just put you on pause for a second. Does everybody fully understand at this point why we're doing this?
Isn't it because you can pretty easily show that x equivalent class times w equivalent class equals y equivalent class times p equivalent class?
Yeah, well, I mean,
So that's also true.
right. I mean, we want to make sure that if we pick up different things from the equivalence classes and multiply them, then we still get the same equivalence class when we're done. Okay, if that weren't the case, we wouldn't have a well-defined multiplication, because if we pick this one here and this one here and multiply them, we get this, and then we pick other things in those classes, we multiply them, we get something in a different equivalence class. We have a multiple valued way to multiply, and we don't want that in a class like this, right? Okay, so so what he's doing is he's picking x and y in the same equivalence class, and picking w and p in the same equivalence class, and then multiplying x and w and showing that you get the same equivalence class as when you multiply y and p. Okay, that's the well-definedness here. Okay, so go ahead with what you you didn't explain on the right there, Eric. That
This?
yes.
That was just me. I essentially, that's kind of defined that if x equivalent class is equal to y equivalent class, if this is true for some m element of x, and I needed to put that because I substituted in for here and here.
But that's also the definition of what it means, right?
Yeah.
Okay, and you have a different m, you know, you have m and n.
Yeah.
Okay, so, and then now you're going to check.
I stuck with what I want, kind of, which is that xw minus yp, and I wanted it over here where it's equal to something times k.
An integer times k,
An
yep.
integer times k.
Okay.
And so then I used the hint and minus xb and added xb in between these two, and then just factored out x. On this one I got x times w minus p plus p times x minus y, or p distributed across x minus y, and then I just substituted in this, so it's x times nk and p times mk plus p times mk, and then I factored out the k, and x and p are both integers, and n and m are integers, so that's also an integer, so that means that the equivalence class of xw is equal to the equivalence class of yp,
Okay,
and
and that's it. Okay, so questions about x? No? Okay, I guess, Zach, are you ready?
Sure.
Okay,
I knocked out part 1 as well.
okay,
I'm supposed to let the function of x into y be a function defined as a relation of x by x equivalence relation on y means that f of x is equal to f of y. Prove that for any x element of big X, that x bar is equal to the inverse image of the set containing f of x.
okay, nicely spoken. That's the way you should say that in a situation like this, right? Okay, good.
So for the initial inclusion, I started out with letting A be an element of x bar.
Can you explain what strategy you're using here then? I mean, because the usual strategy is to pick up something on the left side, show it's in the right, and vice versa. So, but what are you doing here? instead?
Started with this inclusion, and then I saw that I could go back through to get this.
So this is a perfectly legitimate strategy, right? To show that it's in one set, if and only if it's in the other set, right? And that compresses the whole thing. And you have to be careful about that because it doesn't always work, okay? But if you do one direction and look at your argument and it goes in the opposite direction, and be careful to check every single step, right? Make sure you're not overlooking something and don't do it too quickly, right? Okay, so anyway, so go ahead. So
X bar is defined as y is an element of x, then x is in an equivalence relation with y. Thus, x is in an equivalence relation with a, which means from the hypothesis that f of x is equal to f of a, which means that f of a is an element of the set containing f of x. Thus, a is an element of the inverse image of the set containing x. And then, like I said, the logic goes back through that if a is part of that inverse image, it's f of a is part of an element of the set containing f of x.
right, because there's only one thing in there, that's why it goes backwards, forwards and backwards. Okay, questions about this one? Okay, Alex.
Okay, so one is the twisted transitive law. So R is a relation on set X such that R is reflexive for all X, Y, Z element of X. If X is related to a Z and X is related to Y, then Y is related to Z. Since it's already reflexive, you only need to show it's symmetric and transitive, so you show the equivalence relation. And rewriting this statement, the twisted transitive law is if X is related to Z, if X is related to Y and X is related to Z, then Y is related to Z is the transitive law.
Okay, I don't see a proof. When you're rewriting, it looks like you're using symmetry, and I don't see a proof that it's symmetric.
If X is related to Z, Z is related to Y.
Well, that's something involving transitivity. So what's the opening line to show that it's symmetric?
X related to Y, then Y.
Okay, so you're going to suppose X is related to Y, right? So I would go ahead and write that down. I mean, you got to check symmetry. And And the point is that you haven't used the reflexive law, and this actually is not true if you're not given reflexive, right? So the reflexive and the twisted transitive law both together combine to get you that it's actually symmetric. Okay, while you're looking at that, let's see what we got here from Chris. Okay, so then you've lumped them together at the beginning, then you've lumped the product together, and then you distribute it under the bar, and then you have split across the plus, and then you split across times. Okay? Right. So this is really the only, I mean, you could make this longer somehow by going in circles or something, right? But these are really the steps that you need to do. So if you wrote down something different, it's probably because you're not doing things in the, well, it is because you're not doing things in the proper order, right? You're only allowed to use at each stage these two well-defined operations, okay? So that's why it's necessary to take B bar plus C bar and lump it in together. Because only when those are lumped together can you then multiply it with A. And you need to go back and look at, if you didn't do this one this way, then you need to go back and look at the other ones and make sure that you got that in the proper order. Okay, so, and so why don't you go ahead and explain what you did with it. So previously you would have shown that 0 bar acts like a 0. Okay, that is when you add 0 bar to any A bar, it equals A bar. And again, you already have the well-definedness of everything, so you're just using that operation to check. So having gotten that, then this is, I asked him to do the additive inverse part. Okay, so then go ahead.
Explain just that.
Yeah, what did you do in the additive inverse part?
Well, I said for any A bar element of, how do you say it,
Z4.
Z4, there's some negative A bar element of Z4. It's such that when you add them together, then they go under the bar together and then just add to 0.
Right, and 0 bar is the thing that acts like the 0 for this, just like 1 bar is the thing that acts like the 1 for this, for all of these, they're rings, right, all these things. Okay, so basically he's checking that this is a commutative ring, because you have the multiplication and all the axioms that you need. Okay, any questions about Chris's? Okay. So you guys who are done, you can sit or you can stand if you want. We've got only a little bit of time left. Okay. We still got to look at Alex.
I kind of misread the proof. Like, writing it out, I didn't even realize that x was supposed to equal to 0.
Okay, well, can you find two things that multiply together in there to get you 0, which are not 0?
I mean, that aren't 0. I mean, that's, no, not really.
Well, you only have a few combinations there, right?
Right.
What, I mean, you know 1 isn't going to do it, you know 0 isn't going to do it,
Right.
so you got 2 and 3 to worry about, okay? So what's 2 times 2?
4.
Which is?
I guess it's 0.
Mod 4 is 0, okay?
0. Yeah.
So there you go. So write that down. 2 times 2 is 0. So write home that's what you learned in your math class today. Call the dean. Okay. Okay, so we've run into a little trouble here on this one. Okay. Okay, so you got x related to x and y related, but that's still not going to help you because you got to use the twisted transitive law. So, and we got about 2 minutes left, so I'm going to ask you, so there's the twisted transitive law. What is it you want to conclude here? You're supposing x is related to y. You want to conclude y is related to x. Look at your twisted transitive law, okay? What does your twisted transitive law up there conclude?
If x is related to c, then y is related to c.
Then, I mean, what's the thing after your then? What's your conclusion?
Y is related to z.
Okay, so you want your conclusion, you want to use this theorem to get what you have, what you're after, okay? So if you're going to get y related to x, what do you have to do in that twisted transitive law?
I
make this Z so that it syncs up like this.
Okay, and what do you do with Z if you want the conclusion to be y related to x?
You need Z related to what y related to actually need to switch these.
There's no switching. Well, but actually, so Z, you're free to use anything for Z, right? So what would be a logical choice for Z if you want to conclude y is related to x? X. Okay, so your next line should be let Z equal x. Right? It's true for all Z. So you're free to pick whatever Z you want. And so in this case, you're going to pick. And now write out the hypothesis of the twisted transitive law. Just write out the twisted transitive law. What does it now become?